Hello to our coffee corner. I'm Jean-Pierre Chenard. I'm an application engineer and based in Paris, and I will present you how to do a rating factor using OpenBridge. First, I will try to explain what is bridge load rating. Bridge load rating is a process to evaluate the adequacy of various structural components to carry predetermined live loads. Can also define it as defining the live load carrying capacity of the bridge. It can be used to aid in decision between different needs. So, for instance, to put a post limiting the weight of the track crossing the bridge. It can be used also to forecast what the strengthening of the bridge should be. Also, it can be used for permitting. So we create overweight load allowances that can cross the bridge and determine the best route from one point to another point. And finally, as an extremity, it will help us to close the bridge if necessary to maybe at least some tracks, but also for general crossing. You may wonder what is the difference between rating a bridge or designing a bridge. In the bridge design, we provide a more conservative reliability index, and we evaluate the structure for serviceability and durability. Bridge rating it provides a lower reliability index, but for a wide range of vehicles. So it's precisely for different types of vehicle. Though because the weight and the configuration of the live loads are more known, so a measure of uncertainty are reduced. Finally, for bridge design, we take a larger suite of environmental loads, for instance, wind, seismic, all that kind of thing, that we don't take into account for bridge load rating, as we think that this crossing of the bridge will not be in such an environment. If we take in the H2LRFR, the equation for the rating factor, we get that huge equation. But in that huge equation, if you go precisely, it's mainly a simple one with a lot of different coefficients. So, for design load rating, what do we need? The inventory rating level generally corresponds to the rating of the design level of reliability for new bridge in the H2LRFD bridge design specification. But it reflects the existing bridge and material condition considering deterioration and loss of section. It can be used also for operation rating level maximum perceivable live load to which a structure may be subjected. Generally, it corresponds to the rating of the operating level, may shorten the life of the bridge. The legal load rating is just the simplest one. It provides a single safe load capacity for a given track configuration, usually so the legal one, applicable to H2 and state legal loads. It establishes the need for load posting and strengthening. Typically, if it cannot carry the legal loads, we have to diminish the maximum loads or need to strengthen the bridge. And finally, in the permit load rating, check the safety and serviceability of bridge in the review of permit application for the passage of vehicles above the legally established weight limitation. It applies only for bridges having a rating factor superior to 1 for legal loads, because if the bridge cannot carry legal loads, we clearly understand that it will not be able to carry overload live loads. If we reduce the large equation that we had before by just compressing the coefficient that we may have, this can be calculated as the rating factor is equal to the capacity of the bridge minus the dead load demand divided by the live load demand. And each of them, of these different points, can be multiplied by different coefficients that are given in the H2O or taking into account, for instance, live load demands, the dynamic impact or things like that, and different safety coefficients. The ultimate capacity of a bridge, what is it? It's the maximum longitudinal stressing. It means due to normal force, bending moment, vertical shear, supported by the bridge when all materials are at their maximum allowable limit. If the code allows it, it can be in the plastic zone of the material. So you understand that we try to force the different section to go, each section to go to its limit by increasing the normal force or increasing the bending moment, or if we work with shear, increasing the vertical shear until we find the limit, which is the limited stress that we can admit. The safety factor of the structure in design is usually computed using the loaded state with each security coefficient applied to different loads and material capacity. That means that we define already some security coefficient when we apply the different values for the different components for the calculation. There is a specific problem with all damaged structure. A damaged bridge may have reduction in structure efficiency. What kind of reduction we can have? First, it's a reduction of sections. You understand that if we have a steel bridge and the beams are corroded, that the section is reduced and we can take into account only a part of the cross section because the other part is either corroded or has simply disappeared. The other thing is the material alteration, that maybe the concrete, which becomes very old, or steel also, the same way that globally is corroded, so we have to apply some reduction. So in that case, we have to apply reduction coefficient for the computed capacity. There is no rules to determine this coefficient. The only thing that we can do is determine this coefficient by empiric method. So observing, relating the age of different structure with different material with the coefficient that we should take into account. Even we must check all longitudinal forces, so that will bring stresses, mainly stresses to the cross section. So that means bending moment, mz, axial load, nx, shear, vertical shear, qy. We can recognize that live load usually are only generating mainly moment in the deck, and also I should say shear for sure. But the shear value can be neglectable in many cases, but we can have it. In that case, the rating factor for each element can be reduced to the minimum of these two values. Either we have the rating factor, which is the maximum moment of capacity minus the moment due to dead loads, divided by the maximum longitudinal moment due to live loads. Or we can work on the opposite, so we have maximum, but we can have minimum, and is equivalent. So we have another value of rating factor, which is the maximum capacity, the minimum, capacity moment, plus in that case the maximum dead load. Usually it's so the minimum is negative. Okay, so that's why we have a plus, and all this divided by the minimum moment for the live loads. Okay, so this is general overview of what we can have for rating factor. Now, how can we have this in OpenBridge? What is specific? So first we have to define the different parts of the equation. And one important thing is the live load. So for the live loads, we have many possibilities in RM. And the first of them is a wizard, where you have the menu right in front of your eyes, that can create legal live loads directly inside the RM database. So we give these different things, okay, different parameters that you can see, and it will automatically create different things. First, it will create the vehicles. Secondly, it will create the lanes. So we indicate, we have to indicate where are the lanes, but we can take into account the different lanes. So that means that it will also automatically create the influence surface, examine each influence surface with a different track, and do all the superposition of the different envelopes of this using the proper coefficient. The other thing is in the case, for instance, for permitting, or if we want to find out the limit, okay, of crossing, we can input our on track definition. In that case, we can define in lane, because we use inference lines, a succession of axle loads separated by fixed or variable lengths, okay, indicating this. And we can also add uniform loads to take into account other loads, so like standard traffics, but not in the case of permitting. Usually for large trucks, we want to stop the circulation when the truck is crossing the bridge. And you see here the menu where we define for each force, okay? So the distance to the next one, and eventually if we have to take into account specific coefficients that are linked to LRFD. Then we have to compute the ultimate capacity. And in that case, we have two separate scenarios. Depending if our bridge is in concrete or if our bridge is in steel or a composite. Why? Because when using the concrete, it's quite easy to find out the ultimate capacity. What do? We start from a combination, so which will be eventually an envelope of combination in ultimate load, okay, of the bridge. And we will indicate here that we will increase the MZ, okay, until we go to the maximum strain admitted inside the cross-section, which is defined by the code. So from this envelope, you understand that we have an envelope that are directed by different values. So we will take only, I would say, the page where the ultimate MZ is given, so it both in maximum and minimum. And in that case, keeping all the other values, so the same N, the same shear, the same cross moment, and so on, we increase the ultimate MZ to a value corresponding to the maximum strain admitted. And we will store this value into a new envelope, so creating what we call the ultimate capacity, which is an envelope giving for each element the maximum MZ that this element can support. In that case, creating the rating factor is very easy because we just have to output the different values, okay? So we will output in an Excel sheet, and I will show you how we can do this, the different values, so of the ultimate capacity, the dead load MZ, and the maximum or minimum MZ due to live loads. And defining these different coefficients, okay, we apply and find out the value of the rating factor here. And we have to find out the minimum rating factor to rate that bridge. For steel, it's a little more complex because you know that the behavior of the steel is more complex depending if we are in compression or if we are in tension. In tension, it's very easy because we can go until the ultimate strain, okay, even in the plastic area. So this is very easy, okay. But in compression, we have to take into account also other effects, okay, and in some cases, so reduce the maximum capacity, so due to warping of the cross sections or different side effects. So for this, we have a special method inside OpenBridge that will go through different steps. And the first step is we will compute the resistance of each steel section. So giving excuse me, a structure, okay, we store in an XLS the results. So that will, in for each cross section, so of the different steel parts, first indicate the class of the cross section, and from that class, applying different formula, we can find out the maximum and the minimum moment, that is the maximum and minimum moment that the cross section can stand, the steel cross section can stand. Okay, and this gives us a result like that, so an Excel sheet with all these different results where you can see the class and after the different possibility for MY, MZ, and so on. Then we can calculate the dead load constraint. So this is quite easy. The only thing is that this action in RM will store in a specific database all these different values. So it will be after straightforward that we compute the rating factor. So the steel capacity and the dead load constraints are entirely stored in, and you can see it, it's in dbout.lm.rm9. You cannot review it, okay? It's unformatted. Then finally, we can compute the ultimate capacity by element. So this is quite simple because in the XLS, we have the maximum capacity of the cross section. So it will just remove what we have already taken for the maximum ULS combination, okay? And that gives us finally what is the remaining value that we can have. And finally, taking all these different elements, we can compute the rating factor by applying the equation that we have seen just before, applying the different factors for the dead load, for the live load, and the impact factor for the live load. And we will store this both in XLS file, eventually in LST file, and we will see also in diagram. So this is the rating report, okay, where we have these different rating factors that are displayed here for each element, and in the same way we can find out the minimum rating factor to rate the bridge. And to ease the process, we have also in RM the possibility directly to create a diagram of this rating factor, and we have a maximum one and a minimum one, okay, so for these different parts of the bridge. And now we will go to live session to see what we can do. Our first example is a concrete bridge. So this concrete bridge is well known by the RM users, is just the standard 3-span bridge that is is used in the training, okay? And we will use that to rate that bridge. So just as a reminder, so this bridge is a concrete box with variation in the concrete box. We have defined in this some reinforcement, okay, for the cross section. So let me here. So you see the different reinforcement for bending and shear, which are the main that we are using here in this case. And in the analyzer, we can have also, if I put some, I will remove the element bodies. Okay, so we have also press stressing tendon that goes through the bridge, and that should be taken into account for the ultimate capacity, because the press stressing still is not at its limit when we place it. So that means that it can be used as an active reinforcement, I would say, with some reserves in the stress domain that can be activated for giving the ultimate capacity. And now what are we doing? So we do the usual things. So all, in this case, is all the construction different states with all the different load cases, okay? Then we have here the different traffic calculation and superposition that are computed. So using here the legal loads, I should say, okay? So with the track, the tandem, the double track, and the standard loads here apply to 3 different lanes that we place on this deck. And also we use the different traffic superpositions here to finally, at the end, get, in this case, a live load envelope, which is called live sup.load. Okay, then we do the different combinations, okay? And what we will be interesting here is having the ultimate capacity, okay? So here, you know that in RM, ULSUP can be used for different ways. So it can be used for designing the reinforcement if we don't have enough reinforcement. And in that case, it will increase the reinforcement to carry the capacity. And from that, we can also compute the ultimate capacity based on the same envelope. Okay, so I can, for instance, skip this and this, and just recompute the whole thing. So this is the whole scenario with different diagrams. So here we have the inference line calculation, some plots, the live load calculation, and finally, okay, we find out the different checks that have been done. And this is so for the design. And now for the rating factor, what do we need? It's very simple. We just create an RM set. This one, where what do we have in this RM set? So we take it only for the deck, okay? Main guider, because we don't do it for the the piers. It's not necessary. And we output different things. So first, we will input the dead loads, which are stored in STGSum, okay? That accumulate all the dead loads during the construction. And we have also this into 2 envelope, okay? Which is the ultimate moment and the live moment. And sure, we can have this plot, okay, with these different values here. But also what is interesting and more interesting for us is, you know that when we define this RM set, you can also write the result into XLS. And in that case, you should be be careful that to store only at the beginning or the end, because as we have a continuous beam, you will understand that the end of an element corresponds to the beginning of the next element. That's all. And for that, I can write it into XLS. Okay. And if I go, excuse me, I will save this and I go to my directory. Okay, it's on the other screen. If I go into SQL, okay, I can here have the results here. And with the different values, okay, so STGSIM, ultimate sub, live sub. And I just have to compute automatically the rating by adding and dividing these different settings. So if I can say rating, okay, is, so I will not take 0 because it will be infinite. Let's take for this one. So it's equal to the ultimate capacity. So that means it's equal to this one. No, I said, excuse me. I said this one, excuse me, minus the one due to permanent loads. Okay, and all this divided okay, and divided by the live loads. And this gives me the rating factor that can also compute on all the different elements by copying this. And here you see the different values of the rating factor. Be careful, here I took a coefficient of 1. I should also apply the different coefficients that are given by the code at this place. Okay, so very simple in concrete to compute the rating factor. Second example will be the steel bridge. So the same, I took it directly from the training directory of OpenBridge. We have this steel bridge, quite complex. If I put my bodies, maybe you better understand how this bridge is. Okay, so we have mainly two longitudinal beams, okay, here, and we have cross beams, but we will have to check all these different elements for the computation of the rating factor. And in that case, it's simpler, I would say, because we just have to follow the different things. So what we do is, okay, so we have the combinations, and when we go to steel here, you have these different calculations. So you remember in the ultrace we compute the XLS file that will store all the different capacity of each element related to the class. Okay, then we store also in the same database what is given for the self-weight. We could have added also other permanent loads. Okay, so depending on what we can do, we compute the ultimate capacity of the steel, and we finally compute rate F, which is direct to do this. So let's compute this also. Here we have the live loads calculation, which is the longer part in this. It's a little longer because we have many steel elements. Okay, all the cross beams also, we compute all this for each of these elements. The different combination, then the envelope of the combination, and here we compute the steel resistance for each element. We store in the database the Excel file, okay, the value, and reading the resistance value, now again the steel capacity, and we compute the rating factor for the different elements. Okay, and here we have these different things, and we can so see the different output that we have. And we should have a rating somewhere. Still rating. Okay, so we have a listing of the different ratings. Okay, here that we have a rating report with all the different, and easier we can have a diagram. So if we do an RM set for that, RM set, which will be rating, okay, for different element, but if I want to have the full guider, okay, this, in that case, so I put the different elements where I want my rating, okay, and in that case it's in miscellaneous, where in miscellaneous you can store these different elements and ask eventually for the maximum resistance and the rating factor. So if I plot to file here, I see the maximum resistance of each element, both in maximum and minimum. And the next one is this different rating factor. So where the minimum rating factor will be the rating factor of my bridge. Okay, so I expect that this is clear. And as you can see, with OpenBridge, we can rate any kind of bridge because we can compute any kind of bridge, and it's not limited to standard bridges, but we can rate balance cantilever build bridge, segmental bridges, cable stay bridge, so suspended bridge, so whatever we want, either in concrete and steel. And this concludes this presentation.